Vector Calculus, Lecture 25, next to the last lecture. And we're finishing up with Green's theorem. There are two forms of Green's theorem, but we're just going to go over the first of the two forms, which has to do with circulation. So let's just recall, first of all, what is the line integral? You have a curve, C, parametrized by some function r of t, with coordinates x of t, y of t. We're just looking at line integrals in the plane. And the tangent vector at any point is x prime of t, y prime of t. And if we have a scalar function, so we have, here we have our curve C. So this is for t between A and B. You think if this is time, there's a particle which starts out at r of A, and as time increases, it moves along the curve C, ending up at the point r of B in the plane. And in some region that contains this curve, we have a scalar function, or we might have a vector function. So in the case of a scalar function, so suppose f of xy is a scalar function defined on C. Then we define the line integral along C of f of s ds. In terms of the simplest formula for calculating this, this is the integral from A to B of f. So f is a function of two variables that are along the curve. You're looking at points x of t, y of t, times the length of the tangent vector r prime of t dt. And in the case of a vector field, so suppose f of xy is a vector valued function, or a vector field on the curve C, then the integral along the curve of the vector field, I'll just write it f dot dr, is so there's a shorthand. So it's f of xy, it's a vector field, so it has a function f of xy as its first coordinate, b of xy as a second coordinate. There's kind of a pretty shorthand for this, which is the integral f dx plus g dy. But what this means is this is the integral from A to B of f of x of t, x prime of t, plus g of x of t. Let me do this more simply. So on the curve C, f of xy is f of x of t, y of t, which I simply write as f of t. And g of xy is g of x of t, y of t, which you simply write as g of t. So this is f prime of t, f of t, x prime of t, plus g of t, y prime of t, dt. So this is for us, this is the essential formula for writing the line integral of a function along a curve. And let me just remind you what is the fundamental theorem for line integrals, which is analogous to the fundamental theorem of calculus. So a vector field f of xy is conservative if there exists a scalar field phi of xy such that f of xy is the gradient of phi of xy, which means this is the vector field whose first coordinate is the partial derivative of phi with respect to x, and whose second coordinate is the partial derivative of phi with respect to y. And if f is the gradient of phi, and in this case, phi is called the potential function. So a potential function for a vector field is a function whose gradient is the vector field. If phi is equal to the gradient of phi, then along any curve C, the line integral is phi at the endpoint. So you think of your curve C goes from a point R of T, R of A, call that capital A. The endpoint is capital B, which is R at time B. This is phi of B minus phi of A. So this is the fundamental theorem for line integrals. And you observe the value of the line integral only depends on the starting point and the end point of the curve. So for conservative vector fields, the line integral are path independent. So if you had another path from A to B, and you integrate C prime, the integral of the line integral along this path, again, it's just the difference of the value of the potential function at the endpoint and at the starting point. So it doesn't depend on the path. On all of these paths for a conservative vector field, the line integral is the same. This is very similar to the fundamental theorem of calculus, but in two dimensions. Green's theorem is a beautiful theorem that talks about a closed curve. Suppose you have a closed curve. So you have a function R of t. T goes from A to B. And closed means that the starting point and the ending points are the same. So this is a closed curve. This is R at A. You move along the curve, and you end up back exactly where you started. That's a closed curve. And we denote the line integral around a closed curve by putting this little circle in the integral sign. This means you're going around a kind of loop. And so suppose you have a simple closed curve, and which doesn't intersect itself. So there's like an inside, so this is the curve C, and there's an inside and an outside. The inside we'll just call R. And now, if you have a closed curve, you have to consider you can go around the curve in one direction or in the opposite direction. And the positive orientation is the one which, if you imagine yourself going around the curve in the plane, if you're standing facing the direction the curve is going in, your right hand is on the outside and your left hand is in the inside of the region. That's the positive orientation. So if you have a curve with a positive orientation, it turns out that this integral, this line integral, which is sometimes called the circulation, can be written as a double integral. Well, we already saw double integrals early on. A double integral over this region of, so let's see, suppose f of xy has coordinate functions little f of xy and little g of xy. This is a vector field, it has two coordinates. Partial of g with respect to x minus the partial derivative of f with respect to y. And this function in here is called the curl of f, the curl of the vector field. This is the circulation of the vector field. So this is Green's theorem. The first form is the only form I think we're going to consider. So Green's theorem says if you have the integral of a smooth, nice vector field, which is defined in some region containing the curve, the integral around the curve is the double integral of the vector field inside the curve, in the region inside the curve. And so it relates to a sort of like this is sort of like a one-dimensional object. Of course, the curve is one-dimensional, and the area inside is two-dimensional. So this relates a one-dimensional object to a two-dimensional object, which is in itself very interesting. And so let me actually do some examples because, and I'll pick what I think are some of the homework problems. So so we're talking now about section 17.4. And let's look at the first homework problem, which was probably number 17, where we have a vector field F, which is given by 2y minus 2x. So this is my vector field. And I have a region R bounded by y equal the sine of x and y equals 0 for x between 0 and pi. And we want to compute the curl, so we know what it is, and then compute these two integrals separately, just to convince ourselves or show that Green's theorem really is true. Green's theorem says this integral equals this integral, so I'm going to compute both of them separately. Okay, so here is the vector field F. What is the curl of F? So this is my function f, and this is my function g. These are the coordinate functions of my vector field. So the partial of g with respect to x minus the partial of f with respect to y, partial of minus 2x with respect to x is minus 2. Partial of f with respect to y is plus 2, so it's minus 2 minus 2. That's just minus 4. So the curl of f is 0. Sorry, the curl of f is constant. And what does the region R look like? from 0 to pi, this is the sine of x. So this is the region R. So the integral on the right-hand side, the double integral over R of partial g partial x minus partial f partial y dA, this is just minus 4 times the integral over the region of 1 dA. That's just the area of this curve, the area under the curve. What is that? That's minus 4, the integral from 0 to pi sine x dx. That's 4 times the cosine of x from 0 to pi. That's 4 cosine pi minus cosine 0, which is 4 minus 1 minus 1, which is minus 2. It's minus 8. So let me pause for a moment because you need to see if I get this more on the same page. Because as Green's theorem problems go, this is about as simple as an integral as you're ever likely to see. Okay? So we have the region in the plane bounded by the x-axis, that's y equals 0, and sine x from 0 to pi. And if we compute, and we have the vector field 2y comma minus 2x. And the curl of that, partial g, partial x, minus partial f, partial y, is just minus 4. It's constant. So when we integrate the curl over this region, it's just minus 4 times 1. So it's minus 4 times the area. And the area under the sine of x from 0 to pi is 2. So minus 4 times 2 is minus 8. This area is 2. Any questions about that? That's the right-hand side. Let me calculate the left-hand side, and I know the answer has to be minus 8, at least it should be. But let's see if we can do this and check. Okay. So I have my region R from 0 to pi, and this is y equals sine x. And I have my vector field F, which is 2y minus 2x. Now I want to integrate around this closed curve, f dot dr, which is the integral around the curve, f dx plus g dy. We have to understand what this means. Now, we can go around this curve like this or like that. But we want to go around the curve in the positive direction, which means as we move along the curve, imagine walking around the curve, our left hand is inside the region and our right hand is outside, which means it has to be like this. So I want to divide this curve up into 2 pieces. I'll call this bottom piece C1 and the top piece C2. So what is C1? C1 is just the horizontal line going from 0, 0 to pi comma 0. Right? This is 0, 0. This is pi comma 0. C1 is this part of the curve, and C2 is the reverse part. So C1 is easy to describe. Take the function R1 of t equal to t comma 0 as t goes from 0 to pi, we're just moving along this line. And so this integral around the whole curve, I can write as the integral around C1 plus the integral around C2. So I'm dividing the curve up into two pieces, and I have to calculate these separately. So this is one piece, and this is the other piece. So what is the integral along C1? The integral, sorry, this is no longer closed. This is just a line integral. The integral around C1 is, so what is f and what is g? So f of x, y, the vector field, has coordinates little f of x, y, little g of x, y. And if you evaluate that on the curve, on this curve, x of t is t and y of t is 0. So, and what is this? This is f of x, y is 2y minus 2x. So when y of t is 0, this is 2 times 0. And when x of t is t, this is minus 2t. So my function f of t along this horizontal line, this first part of the curve, f of t is 0 and y of t is minus 2t. So this is f prime of t dt. Sorry. This is the integral. So the integral along C1 of f dot dr, that circulation, it's an integral from 0 to pi f of t x prime of t plus g of t y prime of t dt. It's the integral from 0 to pi. F of t is 0. G of t is minus 2t. So this is 0 plus g of t minus 2t y prime of t. But y of t is 0. So this is 0 plus 0, which is 0. So the integral along this line of this vector field is 0. Okay. What about along the curve C? So that's a little trickier. So I have the curve that starts at pi 0, comes around like this and ends up at 0, 0. And this is y equals sine of x. So I could say that R2 of t is going to go from pi to 0. So I could write that as pi minus t. As t goes from 0 to pi, this goes from pi down to 0. And this is, for any pi minus t, this is the sine pi minus t. That's R2 of t. So that's a curve that goes along this arc of the sine function around like this. So this is my x of t, and this is my y of t. So the integral along C2, f dot dr, that line integral. Again, it's the integral, t goes from 0 to pi. Just make sure this is clear. So for R2 of t, x of t is pi minus t, and y of t is the sine of pi minus t. That takes you along the curve from right to left in this direction. And for my function f, the vector field f, this is 2y minus 2x. What is y? Sine pi minus t. This is 2 times the sine of pi minus t minus 2x minus 2 pi minus t. So if I integrate f of t, 2 times the sine of pi minus t times x prime of t, that's minus 1, plus g of t, that's minus 2 times pi minus t, y prime of t, y prime is minus, like this plus, cosine pi minus t dt. So I have to evaluate this integral. And since this is squished together in a way which is very hard to read, and also just to start, just go through it again because this is a little complicated. We have the following picture. We have the vector field F, which is 2y minus 2x. And we have a curve which starts at pi comma 0, moves around the sine wave, ends up at 0, 0. And the way to parameterize this is R2 of t. As t goes from 0 to pi, I want to start at pi and go down to 0. So pi minus t does exactly that. It goes as t goes from 0 to pi, this goes from pi down to 0. And for any given point, pi minus t, the y coordinate is the sine pi minus t. Sine of pi minus t. So if that's R2 of t, then the derivative, R2 prime of t, so this is my x of t, and this is y of t. So if I differentiate these with respect to t, I get minus 1 minus the cosine of pi minus t. And for these values of x and y, 2y is 2 times the sine of pi minus t, and minus 2x is minus 2 pi minus t. So the integral, this is the curve C2, the integral around the curve C2 of f dot dr is the integral from 0 to pi, f of t x prime of t plus g of t y prime of t dt. This is the integral from 0 to pi. F of t is 2 times the sine of pi minus t. X prime of t is minus 1. It's that minus sign. Plus g of t. G of t is minus 2 pi minus t times y prime, which is minus times minus is plus, cosine of pi minus t dt. So we have to do this integral. You see, if we make a substitution, just because to get rid of the pi minus t's, suppose we let u equal pi minus t. So this is just back to calculus. So du is minus dt. This becomes the integral. Let's see, when t is 0, u is pi. When t is pi, u is 0. Minus 2 sine u plus 2u cosine u dt is minus du. So the minus, let me just change these. This is 0 to pi. So we have to compute this integral, which again is just calculus. What is this? This is the integral from 0 to pi. Sorry, the first integral. the integral of minus the sign is cosine. So this is 2 cosine u from 0 to pi, plus, let's see, this integral, 0 to pi, 2 u cosine u du. Let's recall integration by parts. If I have u cosine u cosine u, 1 sine u. So this integral, and 2 cosine u, this is 2 cosine pi minus 2 cosine 0. This is 2 times minus 2, or minus 4. This integral is just minus 4. So let's just look at this. What is this? So I have u sine u 2 times u sine u, evaluated from 0 to pi, minus the integral of sine u from 0 to pi. Sine pi is 0, sine 0 is 0. This term is 0. The integral of minus 2 times the sine is, this is 2 cosine u from 0 to pi, which is 2 times, which is also minus 2 times 2. So I have 2 times minus 2. This is also minus 4. So if you do this carefully, again, this is really calculus review, minus 4 is minus 8. So when we compute the line integral, we got minus 8. And when we computed, that's the left-hand side of Green's theorem. When we computed the right-hand side a few minutes ago, we also got minus 8. So the world is okay, and this is kind of emotional proof that Green's theorem makes sense. And you'll notice it took half an hour to do this problem. These problems are not quick. There's a lot of work to do. But in the course of doing the problem, you get a lot of practice with vector calculus. You have to know how to compute double integrals. You have to know how to compute line integrals. Any questions about this? Let's see. I'll do another problem. That's really, these are, there's skill involved here that, or technique that you have to develop. Let me look at problem number 19 in section 17. So here my vector field is minus 2xy comma x squared. And my region R is the region bounded by the parabola y equals x times 2 minus x and the x-axis. I mean, how do I know this is a parabola? This is 2x minus x squared. It's quadratic. And it's 0 at 0, and it's 0 at 2. And the parabola looks like this. And when x is equal to 1, it's equal to 1. So that's the parabola, and this is y equals 0. So the region is this part of the parabola right here. That's my region R. Let's compute the curl of the vector field and then the double integral of the area. And so this is y equals x times 2 minus x, or 2x minus x squared. So for this function, this is f comma g. So the partial of g with respect to x minus the partial of f with respect to y, that's the curl of the vector field. This is g, differentiate that with respect to x, you get 2x. this is f, differentiate f with respect to y, you get minus 2x. So you get 2x minus 2x, which is 4x. So the curl of f is equal to 4x. Partial of g with respect to x minus partial of f with respect to y. So then the double integral over this region of the scalar function, partial g, partial x minus partial f, partial y, dA. This is a double integral of the function 4x over this region. In this region, x goes from 0 to 2. And for each x from 0 to 2, y goes from 0 to 2x minus x squared. So let me just do this carefully. So the integral from 0 to 2, when I integrate with respect to y, 4x is like a constant. This is the integral from 0 to 2x minus x squared 1 dy dx. The integral of 1 with respect to y is y. Y goes from 0 to 2x minus x squared. This is the integral from 0 to 2, 4x times 2x minus x squared dx. Which is the integral from 0 to 2, 8x squared minus 4x cubed dx. So this is 8/3 x cubed minus x to the 4th. Just integrating this. 8/3 x cubed minus x to the 4th from 0 to 2. So this is 8 times 8 over 3 minus 16. So now we get to arithmetic. This is 64 over 3 minus 48 over 3, which is 16 over 3. So the double integral over this region of the curl of the vector field is 16/3. So this is the right-hand side of Green's theorem. The left-hand side is the line integral of the vector field around the curve. And you have to go in the positive direction. It means you're going like this around the curve. So I need to parameterize that. Any questions about this half? Okay. So let me draw this region again. I'm going from 0 to 2. This way. And then back around this way. And this curve is y equals x times 2 minus x, or 2x minus x squared. So I'm going to write this curve as two pieces. C1 will be this going horizontally and from left to right, and C2 will be going back along the curve like this. So if we parameterize these curves, C1 is what is the curve R1 of t equal to just t comma 0. T goes from 0 to 2. And C2 will be parametrized by a curve R2 of t. So again, t is going to go from 0 to 2. But if you go from 0 to 2, your first coordinate has to go from 2 down to 0. So this is simply t minus 2. And when I put in x equals t minus 2, just note this. If y equals x times 2 minus x, and x is t minus 2, this is t minus 2 times 2 minus t minus 2, which is t minus 2 times 4 minus t. So this is, let me just leave it like that for the moment. T minus 2 times 4 minus t. What is that? This is actually minus t minus 2, t minus 4, which is minus, if I multiply this out, t squared minus 6t plus 8. So this is maybe the hardest part of the problem, figuring out how to parameterize the boundary, these boundary curves. Going horizontally is easy. It's just R1 of t is t comma 0, is moving along this line from 0 to 2. Coming back is a little trickier. You want to go from 2 down to 0. So your x coordinate is going to be 2 minus t. This goes from 2 to 0 as t goes from 0 to 2. And x times 2 minus x, excuse me one second. So t squared minus 6t plus 8. Okay. So let's compute these two line integrals. So the integral along the curve C1 of f dot dr, this is the integral. T goes from 0 to 2. Where's my vector field? Write it down here. My vector field is minus 2xy x squared. So along the first part of the curve, x is equal to t and y is equal to 0. So this is minus 2 times t times 0 comma x squared, which is t squared. This is my function f of t. This is my function g of t along this first part of the curve. And r1 prime, the x dt is 1 and dy dt is 0. So I get, let's see, f of t, x prime of t plus g of t, y prime of t, dt. This is the integral from 0 to 1. F of t is 0, so it doesn't matter what x prime of t is. G of t, which is t squared, but y prime of t is 0. So this is just 0. So the integral across C1 is 0. To calculate the integral around the top part of this curve. Let's do that. So we're going along this curve C2 from 2 comma 0 to 0 comma 0. And this curve is given by y equals x times 2 minus x. And R2 of t is going to be what? So t is going to go between 0 and 2. So 2 minus t. And when x is t minus 2, this is t minus 2 times 2 minus t minus 2, 4 minus t. So this is 2 minus t, comma, minus, we just calculated that, t squared minus 6t plus 8. T squared minus 6t plus 8. So for R2 of t, R2 prime of t, let me differentiate this, the derivative of 2 minus t is minus 1. The derivative of this is minus 2t plus 6. And f, which is equal to minus 2xy comma x squared, for this function, this is my x. X of t is 2 minus t, and y, or y of t, is minus t squared minus 6t plus 8. So this is minus 2 times x, 2 minus t, times y, which is minus, makes this plus, t squared minus 6t plus 8, comma x squared, 2 minus t squared. And therefore, this is t minus 2, t minus 4. So the line integral around C2, f of t, x prime of t, plus g of t, g prime of t, dt, this is the integral from t going from 0 to 2. Let's see, f of t, x prime of t, this is x of t, the derivative is minus 1. So we get minus this. So I can write this as 2 minus this is t minus 2 times this. T squared minus 6t plus 8. Plus g of t. This is g of t. 2 minus t squared times g prime of t. This is g of t. This is g prime of t minus 2t plus 8. dt. Let's see if I can just simplify this in some way. This is the integral from 0 to 2. This is 2 t minus 2 squared t minus 4. This is t minus 2 times t minus 4. T minus 2 squared is the same as 2 minus t squared. And this is minus 2 t minus 8 minus 2t minus 4. Something doesn't look right. I hope I have a minus sign somewhere, because this looks like minus 2 t minus 2 squared t minus 4 dt. So let me just double check this long calculation. So I have my curve C2 moving along this parabola from right to left. The parabola is x times 2 minus x. So when x is equal to 2 minus t, maybe that's where I made a mistake. Oh, yeah, I made a silly mistake there. Let me just go through this again without the mistake. Maybe it should be better. So moving around the parabola, y equals x2 minus x, where x is equal to 2 minus t. As t goes from 0 to 2. So 2 minus x is 2 minus t. And if this is correct, that's just equal to t, 2 minus 2 plus t. So x times 2 minus x is 2 minus t times t. Let's see, I hope that's correct. If R2 of t is 2 minus t, then t times 2 minus t. And this is my x of t, and this is my y of t, which is 2t minus 2 squared. 2t minus t squared. So y is x times 2 minus x. So when x is 2 minus t, 2 minus 2 minus t is just plus t. So this is t times 2 minus t. That's y of t. And my function, my vector field f is minus 2xy comma x squared. So this is minus 2x, which is 2 minus t, times y, which is t times another 2 minus t. And x squared is this squared, t squared, 2 minus t squared. So this is my function f of t, and this is my function g of t. I hope I'm doing this correctly, and we'll see. See, the integral along C2 of f dot dr is the integral from 0 to 2, f of t x prime of t plus g of t y prime of t. It's the integral from 0 to 2. F of t is minus 2t, 2 minus t squared, x prime of t. X is 2 minus t, so the derivative is minus 1, makes that plus. Plus g of t, t squared, 2 minus t squared, y prime of t. This is y of t, 2t minus t squared. So y prime of t is 2 minus 2t. So this is 2 times 1 minus t. So this would be the integral from 0 to 2. See, 2 minus t and t minus 2 squared are the same. T minus 2 squared. This is 2t plus 2t squared times 1 minus t dt. Let's see, before I do this integral, I want to just check again and see where I made it. I have to make a mistake because this is so complicated. So I have x is 2 minus t. T goes from 0 to 2. And the parametrization of this curve, this is my curve C2, moving along the parabola from right to left is 2 minus t times t. So 2t minus t squared. That's x of t. And so x prime of t, if I differentiate that, I get 2 minus 2t or 2 times 1 minus t. Sorry, this is y of t, it's y prime of t. X of t is 2 minus t, so x prime of t is minus 1. So I have the integral of f times x prime is minus 1. G of t times y prime is 2 times 1 minus t. What is f of t? F of t is minus 2xy. So that's minus 2 times 2 minus t times 2 was f of t is minus 2 minus t squared 2 minus 2 squared times t. It's f of t. Times x prime of t, which is minus 1, which makes this a plus 1. So this is 2t, that's this first term, 2t, t minus 2 squared, plus g of t. G of t is t squared, t minus 2 squared, times y prime of t, which is 2 times 1 minus t, minus t minus 1. So that's t minus 2 squared times 2t plus 2t squared 1 minus t, or minus 2t squared t minus 1. So that's exactly right. So I have to calculate this integral, which is just baby calculus. Let's see, what is this? This is the integral from 0 to 2 of t minus 2. You just have to multiply 2 polynomials, I guess. Unless I made some other mistakes along the way. This is t minus 2 squared. This is minus 2t cubed plus 2t squared plus 2t, which is the same as minus 2t times t squared minus t minus 1. I don't know what to do other than to actually do it. So let's see. It's hard to believe this is all the way it's supposed to go. Let's see. So I have t minus 2 squared is t squared minus 4t plus 4. And I'm multiplying that by 2t. So that's 2t cubed minus 8t squared plus 4t plus 8t. So this is 2t cubed plus 2t squared plus 2t multiplied by this, which is t squared minus 4t plus 4. So if I multiply these together, let's see any alternative at the moment, I get minus 2t to the 5th plus 2t to the 4th plus 2t cubed plus 8t to the 4th minus 8t cubed minus 8t squared minus 8t cubed plus 8t squared plus 8t. So this looks like minus 2t to the fifth plus 12t to the fourth plus 2t cubed plus 8t. And I'm taking this minus and integrating this from 0 to 2. So when I integrate, I get minus 2t to the 6 over 6 plus 12 fifths t to the fifth plus 2 fourths t to the fourth plus 8 t squared over 2, evaluated from 0 to 2. This is 1 over 3. So this is minus 2 to the 6 minus 64 over 3 plus 12 times 32 over 5. This can't possibly be right. Plus a half times 16 plus 4 times 4. So the reason it can't be right is because I have a 5 in the denominator. That doesn't make any sense. So this is 8 plus 16. This is 24. Which is 72 over 3 minus 64 over 3 plus this. So something is not right there. Really annoying. Let me see. Maybe I'll come back to this because I don't want to. And if I don't have time to come back to it, I'll write it out correctly and put it on Blackboard. But there's one more thing I wanted to do, having to do with Green's theorem. So this is because we can use Green's theorem to calculate areas in a very clever way. So suppose we take the vector field F to be very simple, just x comma 0. And so this is F and this is G. So G sub y minus F sub x, or the partial G with respect to y, minus the partial F with respect to x. This is 0 minus 1. It's minus 1. So if you look at Green's theorem, you have some region R bounded by this closed curve C. The integral around C, that is this line integral, is the double integral over R of this curl but the curl is minus 1. So this is minus the double integral over R of 1, which is minus the area. So for this vector field, minus the area of the region bounded by the curve is given by this integral. Let's see, what is this integral? This is the integral around the curve, f dx plus g dy. This is f, the integral around the curve of x dx, and g is 0. So we have, if you integrate x dx around the curve, that's minus the area of R. Let's take another very simple vector field. Suppose we take the vector field F to be 0, y. So little f is 0 and little g is y. So the curl, partial g, partial y, minus partial f, partial x. If I differentiate this with respect to y, I get 1. If I differentiate this with respect to, sorry, partial g, partial x. Sorry, I want to take the vector field y comma 0. So the partial g with respect to x minus the partial of f with respect to y. If I differentiate 0, I get 0. If I differentiate y with respect to y, I get 1. I get minus 1. So again, let's see. The integral around the curve, f dx plus g dy, g is 0. So this is the integral around the curve of y dx. This was the integral around the curve of, so this should have been 0x. That's the example I want to take. So the partial of g with respect to x is 1. The partial of f with respect to y is 0. So this is 1 minus 0, or 1. So this is plus. So the integral of f dx plus g dy is the integral of x dy, and that's equal to the area, integrating 1. And here I get the integral of y dx is minus the integral, double integral over r of minus 1 dA, which is minus the area r. So I have that when you have this region R bounded by a curve C, the area A is equal to, on the one hand, the integral around C of x dy, and it's also equal to minus the integral around C of y dx. So the integral around C of x dy plus y dx is 2 times the area of A. So the area of a region A is a half the integral around the bounding curve C of x dy plus y dx. Oops. Let me say that backwards. The integral of y dx is minus the area. The integral of x dy is plus the area. So the integral of x dy minus the integral of y dx is twice the area. That's the formula. So if we look at problem 21, is to use the line integral on the boundary to find the area of the disk of radius 5. So it's always nice to know the answer before you start. If you have a disk of radius 5, the area is pi, area of a circle of radius r is pi r squared. The radius is 5. 5 squared is 25. So we know the area is 25 pi. And the point is to do this integral and make sure and see that we get the right thing. So if we want to parameterize the circle of radius 5, this r of t is 5 cosine t 5 sine t as t goes from 0 to 2 pi. So x of t is 5 cosine t. Y of t is 5 sine t. So the integral around the curve, x dy minus y dx times a half, is 1/2 the integral from 0 to 2 pi, x, 5 cosine t, dy dx is 5 sine t, makes this 25 sine t, minus y, 5 sine t, dx is minus 5 sine t. Oops. Let's do that. Get this right. If x is 5 cosine t, and dy is 5 cosine t, makes this 25 cosine squared t, minus y, 5 sine t, times dx, which is minus 5 cosine t, makes this plus 25 sine squared. You get a half, integral from 0 to 2 pi, 25 cosine squared t plus sine squared t dt. Cosine squared plus sine squared is 1. So I get a half times 25 times 2 pi, which is 25 pi. So it checks. Yep. Okay, let me try and do one more problem. Just try and get some of these things right. So this is in section 17.4, number 25. So we want to find the region bounded by two parabolas. So one of them is r of t is t 2t squared. And the other is r of t equals t 12 minus t squared, which t goes from 0 minus 2 to 2. So the parabola t is 2, 4, 6, 8, 10, 12. So t 2 minus t squared is 2 minus 1, 0, 2. When t is 1, this is 2. And when t is 2, this is 8. So that parabola is like that. In the parabola t 12 minus t squared, when t is 0, this is 12. When t is 1, it's 11. When t is 2, or minus 2, it's 8. So this parabola looks like that. This parabola looks like that. And the region bounded by those two parabolas is this. So we want to find the area using Green's theorem. So let's do it in the form of 1/2 the line integral. If you go around the region, x dy minus y dx. So the region is divided into two parts, the bottom piece and the top piece. Let's call this C1 and the top piece C2. So the bottom piece, this is R1 of t, and call this R2 of t. So along C1, the integral along C1 of 1/2 x dy minus y dx is 1/2 the integral as you go, t goes from -2 to +2, x dy, x is t, dy is 4t, minus y, 2t squared, dx is 1. Okay. That's 1/2 the integral from -2 to 2. 4t squared minus 2t squared is 2t squared dt. This is 1/3 t cubed evaluated from -2 to 2. So this is 8/3 plus 8/3 is 16/3. So this integral from here to here is 16/3. This is C2. The integral around C2 x dy minus y dx is 1/2. And now we're integrating backwards. T goes from 2 to -2. X is t. dy dt is minus 2t minus y, 12 minus t squared, times dx dt, which is 1 dt. So this is minus 2t squared minus 12 plus t squared. So that looks like minus t squared minus 12. So this is 1/2 minus t squared minus 12. I just interchanged this to get rid of the minus sign. 1/2 the integral from -2 to 2, t squared plus 12 dt. This is x dy minus y dx. Minus 2t squared minus 12 plus t squared. T squared minus 12. So this is 1/2 t cubed over 3 evaluated from -2 to 2 plus 1/2 times 12, 6 t from -2 to 2. So this is 8/3 plus 8/3, 16/3 over 2, 8/3 plus 6 times 4 plus 24. If I take 6/3 and 8/3 plus 24, 6 and 8 are 24 over 3 is 8. So I hope this gives me 32. But this is correct. Okay. All right, so this is the tour de force that ends this course in vector calculus. There's more to vector calculus, of course, if you take there's a second form of Green's theorem, and then there are the analogs in 3 dimensions, which are called Stokes' theorem and Gauss's theorem. divergence theorem. These come up constantly in electricity and magnetism if you study physics and you learn Maxwell's equations. That's what it is. Okay. Any questions before we quit for the day? We have our last class on Wednesday, which will be all review, and basically I'll answer questions you have about anything we've done over the semester. I had put a little review sheet on Blackboard to help you prepare for the final. And the final is 1 week from today. Any questions before we go? Not? See you on Wednesday. Bye all.